My name is Dong. You can call me Lilly. I'm currently associate professor here in the engineering science department. I'm tutorial fellow in Trinity College that I run the admission with my colleagues. Trinity is very beautiful. It's a very beautiful college, and we are running lots of sessions in the afternoon. And so please do pop over to have a look. So what I'm going to tell you today about real-time imaging cracks in composites, and this is my research group. We have about 15 people that work on many different types of composite materials. So about myself, because this question, lots of parents came to open days asked me, should we study engineering or material? What's the main difference? I did my undergrad civil engineering. I did my PhD in mechanical engineering. My research fellow position, materials department and metallurgy. And I had my first faculty position in the University of Bristol in the Department of Physics. Now I'm in engineering science as associate professor. So I would like to tell you, don't need to agonize over some of the things. For the parents, if you think about it, do you still remember what you learned in your undergrad? Probably not like 90%, right? So the truth is, I see what engineering here in Oxford is basically teach you how to learn. We have a broad engineering degree that after this degree you're able to learn other things. Same for me. I learned all this after my undergrad degree. So just have a think. Often students thinking, what does engineering mean to you after all? Easier things to see, building a bridge, construction site. What else? Building things? Yeah, just you don't need to, answer, but to have a think about it. What does that mean to you? Like, what do you normally have in your mind about engineering? So, I would like to show you, because my group, we work a lot with the industry. What enthusiasms me about engineering is that I like that my work has a real impact. My work has a real impact in the real world. For instance, my group, we work on aerospace materials with Cross, is a company in the UK, a local company, and Rolls-Royce, National Composite Center, looking like that. I work on semiconductor materials. This is where I found excited about. So you can see we work Element 6, Warwick, and University of Bristol. 90% my funding and research came from nuclear fission and fusion. This is just a few logos that I work with, not all the people I work with. So now, have you ever imagined you want to get a job in nuclear fission, for instance? Yes. Lots of people, by the way, when I do these type of talks for the Oxford online, for year 10, year 12, like that, many people say, oh no, hell no, I'm not going to work in nuclear fission because lots of radiation, it's dangerous. So let me tell you about the work we do in nuclear fission and whether it is, what you thought it is. So my talk is going to come through, I show you different materials. Look, what I'm trying to give you here is I'm going to give you authentic experience about the type of the research. These type of graphs, that's exactly the graphs I use for those international conference research talks, to different experts. So you'll see something like this, nuclear graphite composite, and ceramic matrix composites, aerospace. And here, triazole fuel particles. These are like even 1 millimeter in size, like a poppy seed. I show you some examples how we worked on this material. This, by the way, is not something I'm going to cover today, but just in case you guys are interested in alloys, hydrogen storage, this is where my group work on. Metals, we're testing them at 20 Kelvin liquid hydrogen temperature to solve the problem for hydrogen storage. All of this, all those beautiful pictures you saw, just the colorful things, it's not that we draw by hands. It's actually related to a technique called X-ray computing tomography. I'll show you those, and then I go through those, 3 different types in order. X-ray tomography is like the XCT scans you using, if you break your arm and things like that, you go to a hospital, they let you lying there. The truth is, when you lie down there, you're not rotating around, but it's the X-ray detector that turning, around you. So by doing that, they can collect a 3D reconstruct 3D image of, exactly the structure to see what has happened to the bone. Why the bone always has a brighter structure, brighter color, or more contrast in the picture? Have you thought about it? Because bone has a higher density attenuate more X-rays. That's why when you make a picture out of it, bone is always brighter than the flesh, than muscles. In reality, what we do in the lab, similar principle. This is an X-ray source, and that's the type of sample we use. And this is a detector. But instead of rotating the detector and X-ray source, we turn around our sample 180 degrees, which is much simpler. And the X-ray source we use in the lab is way higher energy than the ones they use, on humans in hospital. So nearby in Harwell, this is something called a synchrotron light source. So basically, what you accelerate electrons to speed of light, and every time they change, they have a beam of X-rays you can explore. For example, my team, we work a lot in Lawrence Berkeley National Lab. That's based in the US. We do travel a lot, looking at their facility. Right here, this is our diamond light source as a UK national facility. Is about 30 minutes drive from here to Harwell. How does the thing work? Basically, this is exactly the same thing we've done. We think it's a hazelnut. And you can see the 3D structure of it, what's inside that otherwise you won't be able to see. So for instance, what you can do, rather than just scanning a hazelnut, you can even take a shell and you squash it. When you squash it, in the same time, every step, you can take an image of the shell and to see how do they fracture. For instance, this type of images, you will see these are the cracks growing through, and you can see which layer of the shell they grow through. This actually sounds very simple, but this is actually the type of process we use to investigate those engineering materials. Here is an example, again, cast iron. You may be familiar with this. Some may you have cooking pots and all that. So we basically make them into small samples like this. We stretch them in the same time we image. You can see how the crack grows in these materials. Okay, this is supposed to be a video, but it didn't play. But you can exactly see how the crack grows. And then when you look at the images, you can see how the cracks link up with the voids and everything. Like this. This is where the things, it's not only about pretty images. All these type of experiments will get end up like terabytes of data. So this is where the modern data analysis, large data, AI, deep learning came in. That's how we use those techniques to look in our work. So the first thing we mentioned, nuclear graphite. That's exactly the thing I'm going to go through quickly. Why do we care about that? So in the UK, if you look at it, it's all over the news. UK, we have aging nuclear power plants, and currently only 5 of them are still generating power station general electricity. So there is a map. I'm not going to go through those, but what's inside of this 4 of those power stations is nuclear graphite. And you may notice, for instance, the nuclear power station in Scotland. In 2018, that was before COVID, they first found lots of cracks in the core, in the reactor core, and then EDF spent lots of money on it and got a better understanding of the core structure of the reactor. But that one was shut down in 2022. But that marks one of the early ones that retired. The rest are gonna retire following that. That's why we have an aging power plant. So what you're looking at inside reactor core is about 10 meters across. When you're looking out there's like a cylinders hollow in the middle. Those are made of nuclear graphite. It's a type of composite. In each core, you probably have over 1,000 tons of nuclear graphite in it. So many people know in a nuclear fission reactor, you're going to have uranium fission. This is where the uranium fuels, they're going to be inside this. These circular ones, those ones you put a boron rod, you absorb neutron, that you shut down the reactor. It's not that you turn a knob and switch off, but you got to put a boron rod in it. You can shut down reactor, stop the fission. So what happened, I'm not going to go through exactly the details in this. This type of structure, they're structural. You have a stack of them, probably 10 stacks of them. The ones in the bottom, imagine if you are at the bottom of the stack, holding another 9 stacks of weight above you. So that will be a lot of weight on you, heavy weight, dead weight. But also this shutting down and temperature gradient, that's gonna cause cracks generating on the K-way roots. If you look at the news, and actually EDF very nicely published the inspection, you can see the cracks all came from the K-way roots. It is a stress concentration area. So when people mention about graphite, they think about graphene, like the fancy material. But you can use graphene to build a nuclear reactor. What you are looking at is about 1 millimeter across this type of material. You got filler particles. It made this coke and coal tar pitch, mix them together, you bake them, graphitize them 2800 degrees. So you generate a bit, so you can even see with your naked eye there are holes in it, 20% porosity in this material. So what you have in this then, you can see the filler particle binder. Different manufacturers, by the way, they make the things differently. They have their raw material from different areas. So their behavior in the nuclear reactor are going to be very different. This is why we study this type of material, understand how do they deform and fracture. When you dig into, for example, this is a big cracks you can see. But if you dug into this, cut into a cross section into this, you see they're micrometer. These are micrometer size, much smaller than a millimeter. There are lots of holes in it. And in nanometer scale, much even smaller, there are even pores in those. So that's what I'm saying. This is a material very complicated. It's not as simple as a block of a carbon. What we do as a research, you don't need to go inside the nuclear reactor to do research. We have the piece of material. We can actually, using X-ray tomography, the XCT thing, image them. And we have ways to reconstruct the pores. You can see blue pores are the one. It's one pore that connected together. And at this smaller scale, you can see they separate, different color means different pores. And at nanoscale, you can look at the shape of them. These are very valuable information when people design the graphite and how they perform in the reactor. That's why we work on this. The other type of work we do on this graphite is that nuclear reactor does not operate at room temperature. In the core of the reactor, the temperature could be 400 degrees currently in the UK, and higher, next generation going to be 750. And the Japanese one operates at 950 degrees. So you got to study your material at high temperature. So in our lab, we have this, furnaces, heating things up, but of course, they're all protected and got the regulations. So we study the material at 1,000 degrees and 1,100 degrees. We look at the mechanical behavior. This is in collaboration with the neutron, X-ray, synchrotron source, and this one is in Lawrence Berkeley lab. I show you the things my students normally work on. They take a tiny sample, about 25, millimeter, 2.3 centimeter, about height half a centimeter. They put a roller between them. They squish them. In the same time, the X-ray going to go through. You squish them, you control things outside the hatch, and then you can image exactly how the crack in that grows. This is exactly the load cell, the device that they've been working with. It's about a meter tall and 30 centimeter diameter, this type of device. This is exactly what the device is operating, and it's behind a cupboard in things. All the control is outside. The samples here, they are not radioactive. They're just normal samples that was made to look at this material. So I show you again, this is where XCT comes in. You see there's a notch, that's a crack. As you press the roller down, we call 3-point bend, you can see the crack gonna start growing. And what you do, you capture the cracks. You can see how they grow, what happens when they grow longer. So the data analysis you got to do is basically you calculate something, the energy you put to grow the crack, and you measure the length of the crack, you plot those as a curve, and you tell the material's behavior, how damage tolerant the material is. So what you have in the end of the results, this is actually literally the figures we publish in journals, in Nature Communications. The strength of the material as a function of the temperature. So for metals, you're going to see the strength of the material gets lower, but this graphite in our reactor core is actually gets stronger at 1,000 degrees C. So this means you can run all your tests at room temperature. The high temperature is going to be a conservative value. So this is something we found excited about. I must show you this graph. I don't expect you to understand this, but that's exactly the thing we said. This is the energy as a function of the increase of the crack length. You plot those together. The blue ones is room temperature, red ones high temperature. You found a higher temperature. This composite, we found that it's more damage tolerant, which is very good news. We don't need to worry, and in our reactor actually behaves better than room temperature. So the power of X-ray tomography is that you can image everything in 3D. You can see that's how the crack grows. It goes, instead of going all the way, like you throw a mug on the floor, it broke into pieces, but this graphite, it doesn't. It goes here, the crack got deflected. Like that. So that's why you needed keep keep going to give it more energy to grow the material. So engineering material in this sense is that we need to understand how our materials behave by doing this type of detailed research. So it's not only about going designing, going building things. It's about understanding the essence of the materials using engineering. So we have those type of little bridges that could bring the material together and make it stronger at. These ones now, I just want to show you. To see these, you can see the cracks actually intact with the graphite, the filler particles. And actually, the beginning when they put those filler particles is actually very useful. You can get deflected, like this. This is exactly why I made the graphite damage tolerant at high temperature. So this is the first time ever these type of images were captured about this material. That's where the work came from my group. I want to mention to you, by the way, there are many different types of nuclear graphite. The graphite I showed you just now is the ones in the UK AGRs. But across the world, the source of material is different. They design something called a fine-grained graphite. You now have seen so much of the UK graphite. You can see these ones, the cracks are very straight. There's no filler particles, kind of the big enough to deflect the crack. That's why we found that these fine-grained graphite, they are less damage tolerant than the UK ones. So when you design your material as an engineer, when you design a material or someone came to you, a material supplier, say, oh, please use our material, you got to be able to judge which one is better. What do you need for a material? So this is where the engineering course comes in. Understand the materials, see whether they are suitable for your engineering application, and you're able to see what is needed in terms of material properties. So these ones, we make a nice pictures like this, but this is a crack linking up with the voice. So this is again a 3D image of the fine-grained graphite, so that they are not as, tortuous as they go. So that's the reason. We have images of nanocrack, the fundamental things. We've gone down to the fundamental things, the nanoscale, to tell the nanocracks that helps supporting the macro behavior. So this is the sort of depth we go into. We work with Argonne National Lab in Chicago to simulate the irradiation using ions instead of neutrons to study the irradiation behavior of the materials. But that's not, you don't need to go, as I said, if you do a job in nuclear fission, you do not need to walk into a nuclear reactor or anything. This is the sort of work we do. I show you something else interesting. Nuclear graphite, that's the core, that's the big blocks. Each one is about 1 meter tall. And these ones, by the way, this is the most popular fuel, nuclear fuel, I think, in the world. They're called triidal fuel particles. It has a kernel. It's about 0.5 millimeter. It got a layer of carbon, a layer of another layer of ceramic, another layer of carbon. The whole particle is about 1 millimeter in diameter. This is the sort of thing we do work on. 3 of my PhD students working on this. So what do they? They put these type of tiny particles into the size of a pebble. Pebble is about the size of a tennis ball. And you can see they are mounted all this area. Those are the graphite I told you earlier about. It's a different type of graphite. But that's how they designed. That's what they call the most robust nuclear fuel on Earth. Because the kernels, that's where the uranium bits are. You can see how many layers they've been encountered. This was invented in the UK in the 1960s. In our lab, we never have the kernel as uranium. We use it as alumina because we study the coatings. The coatings are very important to keep everything. You need to know the behavior. This is a picture of a pebble bed for the next generation of reactors. So what we do, I'll show you something with that. We take a particle, we squish it exactly like the XET. And then, the ceramics, we make sure things are aligned. We got X-ray coming from the left. We rotate the whole thing. There's a furnace, going through argon gas so the carbon doesn't oxidize. And so in the end, what you do, you see this is a little particle. You squashed, and we found, okay, actually room temperature, everything crumbled into pieces like this. So if you're looking at this, at high temperature, by the way, 1,000 degrees, they don't crumble. They started holding together, and you can see there is a main big crack on one side. And that's the triidal particle. So this is something interesting, not a block, but a different geometry. It's challenging to study this, but we got to find ways to look into this. I have 2 pictures to show you this composite. In jet engines, usually you know there are carbon composites in the fuselage, but in engines now, for high temperature, ceramics are much better with high temperature. So there are designs of fiber, silicon carbide, ceramic fiber, symmetric matrix. As I said, if you throw a mug on the floor, it broke into pieces. But like your jumper, imagine your jumper, that's the way. They woven ceramic fibers together. So when you try to tear it apart, you can't. That's why they improve the damage tolerance by these materials and using in jet engines. If you look at, there's one called a Passport. General Electric's Passport is already in use for this. So this type of thing, again, XCT, what you make my people, this is a worker from Lawrence Berkeley. You just take a small samples like this, you press it or you stretch it, and you observe that you see in the XCT what happens. Something may be the fiber cracking, and as you increase the stretch you apply on the material, it goes further, and XCT can tell exactly which bit of things, how is the population increasing, what location in the material. So if some of the industry give you those materials, you can tell them, oh, this one is behaving very well, or it's not behaving as you expected. Why? We're able to tell them why. This is engineering. Of course, you can make nice pictures like this. We call it, I think this picture they've done made it the cover of a nuclear material journal called Evil Smile. It's like the coating outside the ceramics and the fiber holding things together. This is exactly what you need, isn't it? Like in an aero engine, you don't want it to break into pieces, right? So damage tolerance in composite materials. So if you're familiar with a Japanese Fukushima accident in nuclear reactor 2011. This is metal cladding. So the next generation is not only about making aerospace composites. They're using ceramics, making those little tubes. The tube is about 1 centimeter across, could be 2 meters tall, and woven, literally braided together. Silicon carbide is a ceramic, is this type of color, and you've got lots of bundles. You make things like this. My people, what they do, they should take the samples being braided by those famous companies, and we run X-ray tomography on it. We squash them on one side, and we see what's the crack formation on the side outside here. You see those cracks will grow, and they can link up together. You can tell them where the crack goes into the composite and how do they go through the wall of the material. So that's the composite modern state-of-art engineering material we study. So this is the type of 3D images you can see from those things. You can see depending on the design. Look, it's not only about testing. It's about that you gain the knowledge and then inform the material manufacturers how to optimize their material. And that depending on the different types you wave and coating the material, these are the cracks and the pores, and this one is a crack going through the coating layer, distributing outside like that. Don't forget about fusion. When people say nuclear, you only think about fission, but fusion is actually linking things up. I'm not going to go through the details, but I just took, I think, NCC, National Composite Center, based in Fulton in Bristol. They have a very good thing here saying silicon carbide composites enables twice the electricity from fusion generated heat. We want to generate energy, but also want to generate them efficiently. Silicon carbide CMCs, if you're interested, that's a composite material that we study. This is another diagram, just so you have seen it. They make also fibers matrix, but they also get the foams together. So if you study this and you understand the mechanism, you can come up with your ideas, your designs of these materials to form the application, make a fusion reactor more efficient, make an airplane safer. This is exactly how we're targeting while we do our research. A final thing I want to show you, 2 slides on, 1 slide here, and another one showing the materials. Don't forget about electronics. We're not only dealing with the big things. So for example, one of the project we just got funded is that when you look at radar, satellites, and communications, power converters like this, even 6G, although I couldn't even get 4G in Oxford sometimes, but they think about 6G ahead of the time. So what you do is using something called diamond. Everyone knows diamond, it's nice, pretty, but in semiconductor, they're looking using diamond, polycrystalline diamond, man-made diamond, as a heat spreader. When you work your phone or your laptop too hard, it gets warm, right? So exactly, if you have high power electronics, you want to dissipate the heat. If you do not, the device the lifetime gonna reduce. It's gonna break. So a clever way is, can we find something extract the heat away? Diamond. You only know diamonds is expensive, but you probably didn't know they are the highest thermal conductor. Diamonds are hard, they're pretty, but they're also highly thermally conductive. So if you have a piece of diamond holding it, you can cut ice with it. Why? Because the warmth of your hand can be transmitted to the ice very quick to melt it. And we all know Silicon Valley. Silicon compared with diamond, the thermal conductivity is very small. So this is why in the future, you may have diamond all over in your phone, your laptop. Isn't that nice? How do they integrate that? They grow diamonds just like that, the grains like this, and a layer of semiconductor. It's a different type of composite. It's integrating vertically like that. You can see the diamond grains. What we do with them, we use XCT image this. We can tell them, oh, during your growth, there might be some defects and how can you improve it? So we can link up the manufacturer design to the end product quality. So this is something like how we do mechanical testing. You can make a very tiny diamond samples with a big semiconductor on it, and you can see grow a crack to see whether the crack grows through that or deflected. There are lots of engineering mechanics theory behind to support this type of interpretation of the behaviors. So that's all my talk. I just want you to know that engineering is not only about building bridges or the construction things you see. And the nuclear is not only about doing dangerous stuff, radiation. Actually, as education, we teach our students with a broad engineering so they have the ability to learn, to finish the undergraduate degree. They're able to have a dialogue with material scientists, with a physicist, with a chemistry, with anyone that is needed. And then you're gonna keep studying after your undergrad. A lot of exciting things happening. That's all. Thank you very much.